Thank you for the kind introduction, and welcome to my presentation with the title of Consideration of the Correlation between Fatigue Behavior and Fracture Mechanical Behavior in Short Fiber Reinforced Polymers. At the beginning, we have a look at the content of the presentation. We're going to start with introduction and motivation. Then we will go on with methods and materials. Then we're going to have a look at results. And last but not least, summary and conclusion. Generally, the lifetime of each component could be divided into two different main parts. At the first part, we do not have any technical crack in the component. And at the second part, we have already a technical crack in the component, and we have to deal with a growing crack in the component. For the first part, we can use fatigue analysis. And in fatigue analysis, generally, we deal with crack initiation and crack propagation. And the most strong tool for lifetime estimation are the SN curves. But as soon as we have a technical crack in the component, we have to switch from fatigue analysis to fracture mechanics. In fracture mechanics, as I mentioned earlier, we want to estimate the number of cycles before we have a failure in the component. We have also for fracture mechanic analysis different tools, but one of the most favorite one is the stress intensity against the crack growth rate, also crack kinetic curves. The main motivation or the main idea of the presentation is to find any correlation between fractural behavior and fatigue behavior of the material of the short fiber reinforced polymers. The method has been used already for metals, and the main motivation also for metals was that if a material has a better fatigue behavior, it would have also a better fractural mechanical behavior. And we know the fact that during the production, we have always some defects in the material. And in the literature, they use two different approaches to find the correlation between crack initiation part on the crack kinetic curve and the very high cycle fatigue regime on the SN curve, and to find also the correlation between the second regime on the crack kinetic curve, also where we have a stable crack growing in the component, and the high cycle fatigue regime on the SN curves. For this study, we use just the first fracture mode, also just opening. And then here we have a deeper look on the methods which we used for driving SN curves based on the fracture mechanic tests or fracture mechanic data. As I mentioned already, also in literature, they use two different methods. At the first method, they try to find the correlation between the crack initiation part on the fracture mechanic, on the crack kinetic curve, and also the very high cycle fatigue regime on the SN curve. Here we can see the approach. Also, we have two different kind of defects. One of them is rectangular, and the other one is elliptical. And here we have the formula to calculate the stress amplitude for very high cycle fatigue, considering the defect length and also the threshold stress intensity. In the second approach, they try to find the correlation between the second regime and the crack kinetic curve, and also between the high cycle fatigue regime on the SN curves. We see, as I mentioned also in the introduction, we can divide the lifetime of the component into two parts: crack initiation and crack propagation. But considering that from the beginning we have a defect in the component, we can neglect the crack initiation part and consider that in the whole lifetime of the component, we have crack propagation. By integrating the Paris formula from the initial defect size or initial crack length to the critical crack length, and by considering that the critical crack length is reasonably higher than greater than the initial crack length, we can use this formula to find the number of cycles from the startup loading to failure. Here we have a look at the materials which we use for this study. In this study, we use two different short fiber reinforced polymers, once polypropylene with 28% glass fiber, and once polypropylene with 48% glass fiber. The material which we received from our partners were injection molded plates with a diameter of 100 × 80 × 2 millimeter. And the plates had a skin core skin structure. It means that in the both sides of the plates, we have fibers which are highly oriented in the mold flow direction. And in the middle of the plates, we have mostly the fibers which are oriented perpendicular to the mold flow direction. On this curve, you can see the fiber orientation distribution in the direction of thickness. As I mentioned, we have two skin layers on the both sides of the plates, and in the middle we have a core layer. Also, the red line shows the fibers which are oriented in the mold flow direction, and the blue curve shows the fibers which are perpendicular to the mold flow direction. Then we have the geometry and also the position of the specimens which we extracted from the injection molded plates. We extracted the specimens for tensile tests in two different directions to consider the effect of fiber orientation on our calculations. As you can see here, in longitudinal specimens, the fibers are mostly oriented in the direction of loading. And in transversal specimens, the fibers are mostly perpendicular to the direction of loading. The specimens for fracture mechanic tests are extracted from the injection molded plates according to the ASTM E647. Also in two different directions. Once we have the longitudinal direction, in which the fibers are mostly perpendicular to the direction of crack growth, and in transversal direction, in which the fibers are mostly parallel to the direction of crack growth. Then we have an overview on the testing setup and also testing condition. For the fatigue test, we performed the test at room temperature, and the testing frequency was 3 Hertz under a stress ratio of 0.1. And we measured during the test the temperature changes in the specimen to be sure that we do not have any critical temperature increase in the specimen, because we know for polymers, if we have even a small temperature increase, we would have a remarkable changes in the mechanical properties of the material. And also for all of the tests, the temperature increase in the specimen during the test did not exceed 4 degrees Celsius. For the fatigue test, for the fracture mechanic tests, you can see our setup. Also, we performed the test at room temperature under 5 Hertz and a stress ratio of 0.1. And we measured the crack length in the specimen with two different methods, once with moving microscope, also manually, and once with an infrared camera. We developed also a MATLAB code to find the optimum parameters for the calculations, better to say, to minimize the difference between calculated SN curve and also measured SN curve. The parameters which should be or which could be optimized in the calculations are the initial crack length and the threshold stress intensity. We know that for short fiber reinforced polymers, on the one side, the fibers could enhance the mechanical properties of the material, but on the other side, each fiber could be a possible spot for a defect in the material. And also the initial crack length should be maximum at the length of the fibers. Also literally the maximum length of the fibers are 1 millimeter, but we know that during the production process, the fibers will break, and finally the length of the fibers are at the most cases smaller than 1 millimeter. Then we have a look at the results. Also at first for very high cycle fatigue, you can see the stress amplitude for 10 million cycles from the calculations and from the measurements. The difference between the data is in all of the cases less than 10%. Also, I would say the data are acceptable. And the interesting point is that for all the materials and for all the directions, also for both polypropylene with 20 and 48% glass fiber, and in longitudinal and transversal direction, the optimized threshold stress intensity is always 1.12, and which is smaller than the measured one. But we know that with our instruments, we are not able to measure the threshold stress intensity. Then we have the results for high cycle fatigue regime. Here we can see that the deviation between measured ones and also between the calculated ones are higher, but still for a FAIRS study are acceptable, but definitive they have to be improved. The red lines, as you can see, are the SN curves from the measurements, and the black ones are the calculated ones. So summary and conclusion. In this study, we used two different short fiber reinforced materials and tried to drive the SN curve based on the fracture mechanic tests and based on the crack kinetic data. For very high cycle fatigue regime, the method worked better than for high cycle fatigue regime. And also, it seems that the threshold stress intensity is just depending on the matrix, not on the fiber orientation and also not on the fiber content. And in the next steps, we are going to measure also the fiber length distribution for our material. And we are going also to check if the assumption is correct that the crack initiation part is neglectable for the material, and also to use the material, to use the method for other short fiber reinforced polymers. Thank you for your attention, and I would be glad to answer to your questions if there are any.